Hello, Professor.
Hey, how's it going?
Hey, how are you doing?
Good. Do you have anything you want to ask?
Yeah, so basically, it doesn't have anything to do with the test. It's just for ED puzzle. So for the videos, I mean, I went back through them and had to rewatch them. Like, I don't know, some of them I had to rewatch like three times in order to like submit the video. Now, does it matter if I fully submit everything,
No,
or
you
can I
just,
answer the
I think
question?
as long as you answer all the questions, that's all that matters.
Okay.
It'll still have a grade, and that's pretty much what I'm looking at. But yeah, if you just end up skipping around, even if it's a little bit, either forwards or I think even backwards, it will mark it as technically not completed. So
Right.
don't worry about that. All you have to do is just answer the questions. That will count.
Okay, cool. All right. Well, thank you. Bye.
Hey, what's up?
Yeah, so I have some questions. I have some questions about the past homework and also content. So first of all is I was kind of not sure how to do questions 56 and 64 in homework 3, which is chapter 14.
Okay.
So
Chapter 14, you said?
yes. Okay. Yeah. I mean, I have some ideas, but I'm not sure if it's right. Wait, 56 and 64.
Okay, 56. Oh,
So should we? Oh, yes. So for oh yeah, are you gonna read the question?
yeah. So, the main thing you have to do. So, this is from the damping section.
Yes.
So, what you have to do is you have to make sure you use the equation. Now, they want the period. Now, if you go back, let me try and figure out what equation it is.
Is it like 2 pi divided by the omega?
Okay, here it is. So the dampening frequency is equal to the square root of k over m minus b squared over 4m squared. I
Okay.
can't tell what page it is, but it's right before section 14.8.
Yeah. I mean, I could see the formula and I have the slides printed out.
Okay, so yeah, you're gonna end up using that equation, and for the most part, it's a plug and chug. It's actually one of the reasons why I kind of put it in there, even though dampening is going to be a big part of the section. Is that for the most part, if you were going to see it, it would just be plug the numbers into the equation. You don't really have to think too hard about it. Like for example, once we have the frequency, obviously we can immediately get the period, right?
So is that gonna be like 2 pi divided by this omega got from the square root?
Yeah. So it's omega equals 2 pi over period.
Oh, 2 pi over t. So if we get t, it's gonna be 2 pi over omega. Omega. So I got a for. I eventually got period like 0.8981 second.
0.898. Yeah, that sounds right.
Okay. So fractional decrease. Fractional for B is talking about fractional decrease. Is asking for decay constant?
So this is kind of like a phrase that they use. It's one of those examples where they kind of like the way the phrasing they use is supposed to hint at the equation. So they want the fractional change or the fractional decrease in it. So fractional means that there's going to be a fraction, and you're doing the fraction of the change in the amplitude. So what you're going to do is uh, you're going to first figure out what they're going to want you to figure out what the a is. Yeah, so we
Okay.
have an equation for the amplitude per uh, of the wave as a function of time, right?
Yeah.
Yeah, so we can take that equation, and since they want the fractional decrease in it, I want to figure out what the difference is between overall change in the amplitude, which is something like a times e to the junk, right? It's like e to the negative gamma t or something.
Oh, oh wait. So it's a times the negative. of b over 2m because
and then
gamma.
times t, and it's e to the, so like a times e to the negative gamma t.
Oh, it is. Are you saying the equation x equals a to the negative gamma t?
Yeah, yeah, that equation. So it's that with the natural E Euler's number. It's got like a
Yeah.
gamma in it. Yeah, so that is what the amplitude's gonna be over time. And they want it after one cycle, so we can actually change the t to a period. Um, and then what we can do is, again, since they want the fractional change, well, I'm gonna find the difference between what happens to my amplitude after one full cycle and subtract it to the original amplitude.
Why don't we apply the cosine omega t here?
The cosine omega t is the oscillation part. So
Okay.
in the dampening equation, so let's actually go back in the wave equation that basically tells you where a point is at every moment in time. It's amplitude times cosine omega t, right? Where the
Yeah.
cosine is essentially the oscillation factor of like, you know, what's going on in between its points between the amplitudes. Because the amplitude remains the same in a undamped scenario where there's no dampening, the amplitude doesn't change; it just remains constant. But when you start introducing friction and you start introducing this damped oscillations, you're still going to have the same oscillating back and forth between the amplitudes. So you still have that cosine term, but
Okay.
now we have to introduce a what's called a dampening term, which is essentially what's going to start bringing the amplitude down over time. So that's actually what the e to the negative gamma t is. The e to the negative gamma t is the dampening uh, function.
Okay.
So so that term is telling us how much the amplitude is changing over time.
Oh, I see.
Yeah, like we still are gonna have the cosine term, but that's talking about everything going on between. But right now we're just looking at what's going on with the amplitude specifically. So we're not worrying about the cosine. Also, another way to think about it is, since we're looking at it between like after one full cycle, at cosine zero, cosine's at its max value, right?
Yeah.
And then after one full period, the cosine returns to that max value. So in both cases, the cosine ends up being the same value of 1 because that's what
Oh,
cosine is at its at 0 and and after one period.
okay.
So does that make
Uh,
sense?
yeah.
So what we're going to do is to find the fractional change, we want to find the difference between the amplitude, the original amplitude, and the new amplitude after one period. So we're going to only focus on that dampening section.
Okay. So we have to first find the amplitude is the first in the first cycle.
Yeah, let's see. I believe it tells us what the. Oh, actually, so you know what? They don't tell us what the amplitude is, but it actually doesn't matter. We can. It's going to end up crossing out in a second because what I was about to say is that um, after you find the difference, they're looking for a fractional decrease. So we're going to actually divide it by that original amplitude. So all three terms are essentially have an amplitude term in it, so it just drops out.
Oh,
You know what might help? Fractional decrease is essentially, or the fractional decrease in the amplitude is essentially the percent error in the amplitude.
percent error.
Like, do you remember having to do percent error in lab courses?
Yeah, yeah,
Yeah. In the percent error equation, you take the difference between the actual value and the measured value, and then you divide it by the actual value, right?
yeah.
Same idea here, except we're just not multiplying it by 100. We're going to take the difference between the original amplitude and the new amplitude and divide it by the original amplitude.
Oh, oh, okay. So what we're gonna do right now is we're gonna do a e to the negative gamma with t equals 0.
Okay. Keep going.
Yeah, and then find the when t the equals the period, which is like 0.89 we
Yeah.
found.
Yeah. That works. So yeah, you could do a e to the negative gamma times 0, and then then minus a e to the negative gamma capital T period T.
And then are we gonna divide by ae to the gamma times 0? I mean negative gamma times 0.
Yes.
So is the final answer gonna be around 0.33?
Yes. Now, the one thing that you are going to want to include is a sign to dictate whether it's increasing or decreasing, because they kind of left it up. They didn't say. Actually, let me see. All right, you know what? They did kind of call it a fractional decrease, so I guess it would be fine if you didn't, but you should probably get into the habit of using a sign to show whether it increased or decreased.
Um. Okay. So is that gonna be negative 3 over
Yeah.
10?
Mhm.
So in here, should we apply the equation x equals a to the negative gamma t and then cosine omega t?
Oh, you're talking about for the next part?
C. Yes,
Yeah,
C.
for part C. Um, so yes, we're now going to use that equation, but if you notice, they have two different terms. So they have a what's called a initial condition and a boundary condition. This is actually
Yeah.
really common for any sort of question like this where you have the where you're trying to come up with a lot of the variables that they don't tell you right off the bat. So first off, if you notice the very beginning, they get the initial conditions is that when t equals 0, x equals 0. Now that means that even though cosine is our go-to trig function, it's not the only one that has to be put in. We could use any trig function. So I could use cosine or I could use sine. So based off of that first initial condition, which one do you think is more likely to be
I
used?
think cosine.
Which one is 0 when t equals 0?
Oh,
Like which one's,
sine.
yeah, sine.
Sine.
So those initial conditions tell me that we should be using sine as our
Uh,
as the trig function, not cosine.
so just asking, is the function gonna be ae to the negative gamma t sine omega t?
Well, don't forget that there's got to be an e in there. I feel like you keep dropping the phrase e,
Yeah.
but there so it's a e to the negative gamma t and then sine omega t.
Oh, yeah. Okay. Yeah.
Yeah, so we have gamma, we have omega. The only thing we don't have is we don't know what a is, and that's where the boundary condition comes in. So
Oh.
the next thing they say is that at t equals 1, our position, our actual position is 0.12. So what you're going to do is you're going to plug those two numbers in for t and x, and then also plug in what we know about gamma and omega and solve it for a.
Okay. So, Mr. Klaus, so in here is the cosine on the calculator. Should I use radian or degree here?
Radians.
Okay. So the amplitude is gonna be around 0.2366, right?
Yeah.
So the function's eventually gonna be xt equals 0.2366 e to the negative 0.3964t and then times cosine 7t.
Well, remember It wasn't cosine.
Yeah, sorry, sine. Oh, wait.
Yeah, you might want to actually double check that amplitude.
Oh, so A is gonna be around 0.2715. So X is gonna be like 0.2715 e to the negative 3964 t power times a sine 70.
What was the amplitude again?
Um, approximately 0.2715.
Oh, okay, yeah.
64, I feel I have no clue how to do it.
64.
Yeah.
All right. So with 64, so it kind of already shows or hints at what you're supposed to do. First, it tells us that we have to use equation 14-23. So go back earlier, and that's the equation for the amplitude for a forced oscillation.
Wait, 14-23. What's that equation?
It should be,
The textbook.
yeah, it should be in the textbook. It, I don't know if I wrote it in the notes.
Oh, wait, is that the A0 equals F0 over that long
Yeah,
thing?
yeah, that one. So they want us to differentiate that, and they want us to show that it peaks at a certain frequency. So what that means is we want to differentiate that with respect to omega, and then solve for it for when it equals zero. Because remember how, like in calculus, you know that when you take the derivative of something and then you set it equal to zero, that tells us either one of the high or low points of the graph.
Oh, yeah.
Yeah, because that's going to be where the part where the slope equals zero. That's what you're doing. So you're going to differentiate that. Now, the best way that I could recommend it is first ignore the F and M for a second, but you're gonna rewrite see all that garbage on the bottom with the omegas.
Oh, yeah, garbage.
Yeah, you're going to move that up to the top. So you're gonna like you know how when you have something written underneath the radical, you can rewrite it with a square root, like sorry, with a to the 1/2 power.
Uh, yeah. Oh, you mean like write the square root as a 1/2 power?
Yeah. And since it's in the denominator, we can change the power to a negative, and that
Yeah,
way it brings it up to the top.
yeah.
That's going to make life a lot easier because then we could use the chain rule to figure to derive to take the derivative with respect to omega.
Okay.
And annoyingly enough, we have to kind of do the chain rule twice because we have the main part with the main square negative square root. But then inside of that, we also have another power. So yeah, there's a whole lot of chain ruling going on.
Okay. So you mean we have to differentiate this A?
Yep.
Differentiate like with dA d omega?
Yeah, dA over d omega.
Mr. Clark is still there. Yeah. So in the parentheses, the omega 0, when I differentiate, is that gonna be a 0? Become a 0?
No, okay, yes. Okay, so the you're talking about the omega. So like when you do the chain rule for the inside part,
Yeah.
so the square comes out. Then you have the the same term of the omega squared plus omega naught squared. Then when you take the derivative of this stuff inside, yes, the omega naught squared ends up being zero because it's a omega naught is a constant.
It's really a long derivative. So yeah, so I just differentiate the dA over d omega. So what's next?
Set it equal to 0.
Oh, the derivative. Okay, yes. So, so what's the next?
You set it equal to 0.
Yeah.
That should be it. Solve for omega and try to get, because the whole point is to try to get it to look like the equation they showed you. Omega equals omega naught squared minus b squared over 2m squared.
Okay, so like for the f naught over m, we can just like put it to the other side, make it times 0, right?
Yeah.
I mean, cause I mean, like at the beginning, I wasn't sure how to eliminate this f naught over m. Yeah. Oh, so f naught over m are just like constants, right?
Yeah.
Oh, I see.
You just multiply and divide it to the other side, and it just drops out.
Oh, okay. Oh, Mr. Claudia, there's another thing. So so in the simple harmonic motion module, sometimes I see the x velocity and acceleration functions only contain, for example, x only equals I mean like v only equals a times omega, and sometimes it's like a times, I mean like negative a times omega times sine. Do you know like in what situations do we only need to apply a with omega?
Talking about you're saying the velocity for the simple harmonic motion?
Yeah.
Yeah, that's the max velocity.
Oh, so the max velocity is only a times, negative a times omega.
Well, technically, it's just the a omega. The negative sign part is the how it oscillates over time. So it's kind of like essentially it's like amplitude.
Okay. Oh, yeah, Mr. Klein. Another thing is when I look at the resonance slide, there's basically in resonance and I believe the damp harmonic motion, they have an they have an equation of motion like m to the second derivative of x plus b to the first derivative of x, and then kx equals f naught cosine omega t. Um, I'm not sure like and what is this equation using for?
Say that again.
So basically, what's the equation of motion using for?
Which one?
Uh, so on the slides of damp harmonic motion and force oscillation resonance, they both have the equation of motion appeared,
Yeah.
which
So
is
if I'm gonna pull up the slide right now, but I'm pretty sure it's for the specific type of motion. So, for example, we have the a cosine theta, which is the equation of motion in in the ideal case, and then when we start adding in more complex scenarios like it being damped versus being driven, the equation becomes a little bit more and more robust. So you're talking about the m uh, d squared x over dt squared
yeah,
plus.
yeah,
Yeah, so um, the equation that we have, the a cosine omega t and all the other ones, technically those are considered one solution to the equation of motion. So if you actually look back in the slides, let me. Okay, so if you look back pretty early, I think it's page 12.
well,
It's it's where I have the sum of f equals ma, and
yeah,
I said that uh, by using the setting equal the net force equal to the spring force, we can get this equation of motion that basically says that m times the second derivative of x plus kx has to equal 0.
Oh,
Now, what that means is that any object that is in simple harmonic motion, if we want to get an equation that to represent its motion, it has to satisfy that condition.
okay. Wait. So on the equation of motion, which adds b times dx over dt, isn't that just gonna be like b times dx over dt equals f naught cosine omega t, because the other two plus each other
So,
are gonna be
uh,
zero.
here what we end up having is so now this kind of goes with the idea that I said that it starts becoming a little bit more robust. Now we end up having that damp term involved. So the equation that we had before no longer satisfies the condition. You know what? Maybe this it might be better that this is we call this the condition for motion,
Okay.
because the equation of motion that we use for a damped harmonic oscillator now has to satisfy this condition. So that's why we end up having to include this e to the negative gamma t.
Okay.
So that now we end up having a second derivative, a first derivative, and a non-derivative term all in the same equation. And we have to somehow get it to once again equal 0.
Okay. What's this f naught cosine omega t standing for?
So that is for when it's a forced oscillation. Again, it's just one of those things where it further brings the equation more and more prolonged. So this equation you can almost think of as being the absolute equation, because now we have every single possible thing that could happen. We have an object experiencing a spring, which is where the kx is. We have an object that is experiencing damped oscillations, so it's being affected by friction, and it's also being forced into its oscillation. So something is mechanically driving it.
Okay.
So it goes back to the same idea that there has to be an equation that I can plug in for x and substitute its first derivative and second derivative that will allow me to solve this equation. Again, this is a condition that whatever equation I come up with for my oscillator has to satisfy. Now, the equations that I write underneath it, the in this case the x equals a naught sine omega t plus phi, that is a single solution to this condition equation.
Oh,
Yeah.
okay.
So, like I said, the derivative that I give you in those setups, they're conditions. They're not equations that you actually use on the fly, except to test to see if a certain equation is a viable simple harmonic motion solution.
Okay.
Uh, for example, uh, going back, if you decide that you want to go back to I think the base condition one, the one that only had the second derivative and x from earlier in the slide. I think a second solution that also works is something with like a e to the um, like negative omega t or something. I forgot the exact equation. I think it actually might be one of the homework questions. Which one? This is chapter 14, right?
Yeah.
Let me just check real quick. I might have had it as I might have had it a while ago, or maybe it pops up later. But I did have a question that was essentially like, take this equation and check to see if it is a possible solution. And you end up seeing that it does satisfy the that condition equation that we have. So there are other equations for simple harmonic motion. The a cosine omega t is just the simplest equation that we have, but it's not the only one that we have.
Oh, I see. Okay. What does underdamped mean in the summary?
Let me just double check. So in here, the underdamp. So if you actually go to section, it says page 36. I mentioned what underdamped, critically damped, and overdamped basically refer to. So in the underdamped case, that basically means that it still oscillates a few times before it actually comes to rest. So, um, with a lot of these cases, you can actually if you have a screen door, you can actually play around with the settings on that little air canister in order to get all of these effects. So like an underdamped scenario would be one where you try to close the screen door, it begins to close, then it stops, and then it begins closing again, and then stops, and almost opens up a bit, and then closes, and then stop, and then opens up, and it does that. It like oscillates a few times, but then it does eventually come to rest.
Oh, okay. Maybe I will double check the video.
Yeah, and then like the other ones, critically damped and overdamped, basically just refer to how quickly it comes to rest. So like critically damped, there's no oscillations, uh, but it but it does come to rest like right away. And overdamped means that there's so much friction that it just takes forever to come to rest. But once again, there's no oscillations.
Okay. Uh, Mr. Cloud.
Yeah, what's up?
Okay. Uh, so another another part is at the wave, like chapter 15 about the wave.
Okay.
Yes. Um, so I don't know if you could explain this a little bit, but what I'm feeling kind of confused is why does this chapter mention about pressure in the study? Because in my mind, pressure is only about like air pressure or pressure in the fluid. How can pressure do anything with the waves?
Because that's what longitudinal waves are. Longitudinal waves, like in sound in particular, are essentially sections of pressure, high pressure and low pressure.
Oh,
Yeah, because the way sound wave propagates. Okay. Yeah, so the way that the sound wave propagates, it you'll end up having these areas where the molecules are really close together and other areas where the molecules are really far apart. And that in particular is just pressure. Like,
oh,
yeah. Um, Now, I was actually now that I'm looking at this, this is the chapter. Chapter 15 is the one where you'll see the what I was talking about, how there are other equations that satisfy these wave conditions. So if you actually look in this chapter, I basically do the same thing where I tell you the one-dimensional wave equation, where it's like the partial second derivative with respect to distance equals 1 over v squared partial derivative with respect to time.
Yeah.
So once again, just like before, this is a condition that basically says that if we have an equation that is supposed to represent the position along a wave, then it has to satisfy this condition.
Oh.
So, for example, the equation a equals cosine omega t would not satisfy this equation, because
Yeah.
the partial derivative with respect to x would be 0, and then we would end up having 1 over v squared times, and then the second derivative with respect to time. So it wouldn't really be a solution to that. So that's why we end up having to change the equation to end up having a kx term and a minus omega t term. But as I've mentioned, there are other equations that would satisfy that condition. So later on, one of the homework questions basically has you do that, where they give you a new equation, and now you'll have to see, does this equation satisfy the wave condition?
Okay. Yeah, and another thing is, we like in this chapter it even mentions partial differentiation, but isn't that something we're gonna learn in calculus 3, which we haven't even learned yet?
Yeah, I mean, it's not something that you're going to be doing on the test, but you should still have an eye for partial derivatives. I mean, they're pretty straightforward. All it really means is that you're just not going to what's it called? Um, Sorry, I just completely blanked. You're not gonna really worry too much uh, about the other terms. Like, you just, when you do the partial derivative with respect to x, that basically means that you ignore the time parts and you just consider the x as your variable. Same thing with the time.
Okay. Okay. Is there gonna be a question on the test asking us to do something similar as question 64 in chapter 14, which we're gonna do this complicated differentiation?
Uh, Probably not.
Oh, okay. Thank you.
On tests, like I said, I don't think that there's any derivatives that you have to do on the test.
Okay. Thank you. And also the test on next Wednesday is gonna be a midterm, right?
No, it's still going to be a test. It's going to be the same thing as the other ones. It's
We
the
only
second part.
we only test two. I mean, like these three chapters.
Yep.
Wait, so when's gonna be midterm one then?
Never.
Wait,
Um, yeah, I said before that what I did was I took the midterm and I split it in half. So test
oh,
one and test two are midterm one.
oh, okay.
Yeah. So had this been a normal year, next Wednesday would have been when you take your first midterm, and it would have been both these tests together, which is
Wait,
why the practice test has 4 questions instead of two.
wait a minute. Wait a minute. Do you mean on next Wednesday? Which I mean, didn't you say at the beginning on next Wednesday there's only gonna be tested the on 14 to 16?
Yeah,
Oh, okay. And then I mean, I feel a little confused. Why do you suddenly say is about the midterm 4 questions?
like I said, normally my midterm
Oh,
is 4 questions, but because I don't want you guys having to block off such a large part of time, because things happen, and sometimes it's hard, with things at home, it's easy for people to get distracted. So
oh yeah.
I split it into half, so it's smaller chunks.
Oh, okay. I understand now. Thank you.
No problem.
Mr. Cloud, do you mean normal times, if the pandemic is not occurring, this
Like,
summer session is gonna be in school?
so like if so I don't think it would be this year, but next year most likely we would start meeting in person. In which case, uh, I would go back to the typical, you know, combining the tests into one big midterm.
Oh, okay. In person means everyone needs to go to the school, the university, in the classroom, right?
Yeah, that would be what. Yeah, if we're all like going into the one of the classrooms.
Okay. Yeah, Mr. Cloud. By the end, I, just asking. When, for example, in the weekends, if we don't have a meeting session, can I ask you any questions by like text message?
Say that one more time.
So, in during weekends or days that we're not meeting on Google Meet, if I
Yeah,
have a
send
question,
a message through email.
I mean through chats, right?
Yeah, because I think you could do it through like an email chat.
Yeah.
Yeah.
Oh yeah. Okay. I think that's all. That's all my question today. Thank you.
Okay, no problem. Let me know if you have any other questions.
Yeah. Okay. Thank you, Mr. Cloud. Have a good weekend. See you later.
Anytime, you too. Bye.
Yeah. Bye.